Yeah, so today I'll be speaking about a few different results in this area, spanning a few different papers, most of which is joint work with Asaf Ferber. So this slide is probably not necessary, but just in case, let me start by telling you what a hypergraph matching is. So a k-uniform hypergraph is a generalization of a graph where instead of the edges having two vertices, each edge has exactly k vertices with some general k. So here's a picture of a three-uniform hypergraph. And then a matching in a hypergraph is just the collection of edges in that hypergraph which are pairwise disjoint. So no two of the edges are allowed to intersect. And a matching is a perfect matching if it covers all the vertices of the hypergraph. So here, this particular three-uniform hypergraph has a perfect matching. And of course, a necessary condition if you'd like to have a perfect matching is that the number of vertices of your hypergraph needs to be divisible by k, by the uniformity. Okay. As probably most of you are aware, in the case where k equals 2, which is the case of graphs, we really know a lot about matchings. We have a very powerful and well-developed theory of matchings. But in the hypergraph case, matchings become a much more difficult thing to think about. And in particular, I guess just to illustrate this, the problem of deciding whether a hypergraph has a perfect matching is one of the most classical NP-complete problems. So for various reasons, hypergraph matchings are interesting and challenging things to study, and it's very natural to ask about perfect matchings in random hypergraphs. Yeah. So when one thinks about perfect matchings in random hypergraphs, maybe the first theorem that might come to mind is this famous theorem of Johansson, Kwan, and Wu, which it gives the threshold for existence of perfect matchings in random hypergraphs. Essentially, it characterizes when you should expect a random hypergraph to have a perfect matching. So just to go through this theorem, so my model of random hypergraph is the binomial model, where I've got a fixed set of n vertices, and meaning there's n choose k edges I can have, and each one of them I want to put in the hypergraph with probability p independently. And then this theorem is that if the number of vertices is divisible by k, which it must be to have a perfect matching, and if the edge probability is not too small, namely if p is at least n to the, well, at least a large constant times n to the k minus 1 log n, then your random hypergraph is very likely to have a perfect matching. Yeah. And this condition on p is essentially best possible. This is a threshold in the sense that if p was smaller than this, if p was substantially smaller than n to the k minus 1 log n, well, then you'd have a random hypergraph with about, with fewer than n log n edges. And by coupon collector problem type reasons, I mean, if I'm throwing in fewer than n log n random edges, I'm probably going to miss some vertices. There's going to be some isolated vertices, and so I can't expect to have a perfect matching. Very good. So this tells us, except right at this critical value, when random hypergraphs have perfect matchings. Yeah. As I said, this is a famous theorem. This is also known as the resolution to Shamir's problem, and I guess until before 2008, before this was a theorem, this was one of the most notorious open problems in the theory of random graphs and hypergraphs. Of course, now this is a solved problem. We have a proof thanks to Johansson, Kwan, and Wu. But I'm here to tell you today that this is not, I think, not the end of the story as far as perfect matchings in random hypergraphs are concerned. And there are a variety of different problems in this area which remain very challenging, even after Johansson, Kwan, Wu, and the things we now know how to do for perfect matchings. Roughly speaking, the limitation of the proof of Johansson, Kwan, Wu, and in fact all proofs that show perfect matchings exist at really anywhere near this threshold, is that they're in some sense quite non-constructive. They have some way of showing that random hypergraphs have perfect matchings without really being able to get your hands on the perfect matching. So yeah, so today I have a couple problems to talk about in the subject of perfect matchings in random hypergraphs, where it does seem that very substantial new ideas are necessary. So that's the plan for today. Okay. So the first topic I would like to talk about is Dirac-type theorems in random hypergraphs, which I think this topic itself needs a little bit of introduction. So let me start here by reminding you of probably the two most classical theorems in extremal graph theory, namely Mantle's theorem and Dirac's theorem. So Mantle's theorem, it's telling you how many edges you need to have to force the existence of a triangle, namely if you have any n-vertex graph, equivalently a subgraph of the complete graph Kn, and it's got at least, well, it's got more than n squared over 4 edges, which is about half as many edges as you could possibly have in an n-vertex graph. Then you've got a triangle. And Dirac's theorem tells you that if you have any n-vertex graph whose minimum degree is at least n over 2, then you have a Hamiltonian cycle. You've got a simple cycle which runs through all the vertices. Okay. Yeah, so these are very classical and very interesting results. But for me today, one particularly interesting fact about both of these theorems is that they hold for robust enough reasons that in fact both of these theorems also hold, well, at least a version of these theorems also holds inside random graphs. So here is what I mean by this. This is a random version of Mantle's theorem and a random version of Dirac's theorem. So let's look at this. So I want to consider a random graph. I've got n vertices. Each of the n choose 2 edges is present with probability p, meaning that, I mean, unless p is really tiny, and we won't worry about that, this thing is likely to have about n choose 2 times p edges, and the degrees are likely to be about n minus 1 times p, because each vertex has n minus 1 possible neighbors. Now, the random version of Mantle's theorem, which was proved by Frankel and Rödl, is that if you have a random graph with not too small edge probability, namely somewhat larger than 1 over root n, then your random graph typically has the property that all of its subgraphs with sort of whose relative density exceeds well, a half, so which have at least this many edges. So like a bit more than a half fraction of the edges of the random graph, all of those subgraphs have triangles. So hopefully it's clear in what sense this is a random version of Mantle's theorem. It's like a version of Mantle's theorem relative to a random graph. And similarly, for Dirac's theorem, it was proved by Lee and Sudakov that if you take a random graph, again, whose edge probability is not too small, then typically you have the property that if you take any spanning subgraph with at least this minimum degree, so it's like the relevant, it's like the corresponding fraction of the minimum degree of the random graph itself, then you have a Hamiltonian cycle. Okay. So hopefully from these two examples, you sort of get an idea of the kinds of questions one may be interested in here. But just to summarize, sort of the meta question here is that we would like to understand to what extent our favorite extremal theorems still hold in a noisy environment of a random graph. Yeah. Yeah, so to very quickly give you some background in this area, I mean, this is an enormous topic. It was started by Frankel and Rödl. There's been tons of work by tons of people, unfortunately more than I can really cite on a slide. But in particular, I would like to highlight, well, sort of within the last 5 years or so, there's been really dramatic progress in this area, thanks to the discovery of 3 very powerful and very general methods for attacking these kinds of problems, namely transference principles, multiple round exposure techniques, and hypergraph containers. So right now, I won't say too much about what any of these, I won't say anything about what any of these are. But yeah, at the sort of, when some of these ideas were discovered, they were sort of powerful enough to resolve a huge number of problems in this area sort of all at once. So this is now, I think, quite a mature area. One exception, one type of problem which is not really that amenable to these general methods is problems about spanning substructures. So if you want to ask things about like Hamiltonian cycles or perfect matchings, these kinds of questions don't sort of follow as immediate consequences of these general methods. And there's still lots of interesting things to ask about that. Yeah, so maybe you can guess where I am sort of going with this talk, and I'd like to ask questions of this type. I'd like to prove theorems of this type for perfect matchings in random hypergraphs. Yeah. But before I start talking about perfect matchings, I'd like to sort of show you one, I think, particularly striking example of what you can do with some of the general methods that I mentioned, which will sort of motivate what's coming next. I want to tell you about relative versions of Turan problems for hypergraphs. So let's just remind ourselves what Turan numbers are. So the extremal number NF of a K-uniform hypergraph F is just the maximum possible number of edges you can have in a K-uniform hypergraph on n vertices, which does not contain a copy of F. So these things are important parameters. Generally, one wants to think about them asymptotically. So one defines this asymptotic parameter, the Turan density. Pi of F is the limit as n goes to infinity of xnf over n choose k, which is like the maximum possible density of edges you can have in a hypergraph which does not have a copy of F. Now these parameters are, as I'm sure you know, these parameters are very extensively studied. It's a central problem to understand these. In the case where F is a graph, we know everything. We have a formula for the Turan density. But the hypergraph case appears to be much more difficult. And for example, even essentially the simplest non-trivial case, the case of the Turan density of the complete 3 uniform hypergraph on 4 vertices is for example unknown. Yeah. So we're very far from having like a complete understanding of the Turan theory for hypergraphs. And one may think, well, we had better understand the Turan theory for hypergraphs before we have any chance of proving relative versions relative to random graphs. But I think quite surprisingly, it's actually possible using the methods I just mentioned to prove relative versions of Turan type problems, even when we don't actually know the answer to these problems. So this theorem was proved, well, it was in one of these papers. There was some independent work by Conlon and Gowers and by Schacht, where they proved 1 million theorems about extremal theorems relative to random set. And this was an especially nice one, which says that the sort of what you'd expect, that if you have a random hypergraph with not too small edge probability P, I'm not going to tell you what not too small means, then typically this random hypergraph has the property that all of its subgraphs which sort of exceed the Turan density, whatever that Turan density is, and in general we don't know, all of those subgraphs have a copy of it. Yeah. So you should perhaps think of these kinds of methods as like a black box way to take an extremal theorem and just like spit out a random version of that theorem. You don't necessarily need to know anything about how to prove the extremal theorem. So, yeah. As soon as you can prove a Turan type theorem for random hypergraphs, you immediately have a relative version of it. Okay. Very good. So now let me finally start talking about perfect matchings. Let me tell you about the extremal problem that one one generally considers for perfect matchings. So I guess the notion of degree in a hypergraph is that for a set of vertices S, the degree of S is the number of edges of my hypergraph, which include S. The point here is that, in a graph, it only really makes sense to talk about the degree of a single vertex. But in a hypergraph, if you want, you can talk about the degree of like a pair of vertices, the number of edges, which include both of the vertices in that pair. And because it makes sense to talk about degrees of sets of vertices of different sizes, you sort of, there's no single most natural notion of minimum degree. You actually need to parameterize your notion of minimum degree if you're going to talk about hypergraphs. So for any number d, I guess d needs to be less than the uniformity k. The minimum d degree of a hypergraph is just the minimum of all degrees of sets of d vertices. Okay. And then the parameter that we are interested in is mdkn, which is the smallest m such that every n vertex k uniform hypergraph with minimum d degree m has a perfect matching. So how large does the minimum degree need to be to guarantee the existence of a perfect matching? So of course, for this to make sense, you need the number of vertices to be divisible by k. Okay. Yeah, so just like for Turan problems, we're generally interested in asymptotic questions. So it makes sense to define a limiting version of this parameter. The limit is n goes to infinity of this parameter over n minus d, choose k minus d, which is the right normalization here because, I mean, if you have a set of d vertices, its degree can be at most, well, there's n minus d other vertices, and you have to choose k minus d of them. Okay, and very much like Turan parameters, like Turan densities for hypergraphs, there's been a lot of work on this stuff, and it appears to be a very difficult topic to determine these Dirac limits. For example, I think that the smallest case that is unknown is the 6 uniform case. If you have a 6 uniform hypergraph, how large does the minimum degree need to be to force the existence of a perfect matching? Yeah, so there's actually some very interesting connections of between these kinds of questions and some seemingly unrelated probabilistic questions. Maybe I won't talk too much about that. Yeah, so I mean, everything is very much analogous to hypergraph Turan problems in that, you know, we have this extremal parameter that we don't necessarily have a good understanding of, but emboldened by what we just saw, we may, it still makes sense. We can still try to ask for random versions of Dirac-type questions for hypergraphs. So here is the conjecture. I guess by now it's the 4th time we've seen something like this. So very briefly, it would just be saying that for a random hypergraph whose edge probability is not too small, typically that hypergraph has the property that if you take any of its subgraphs whose sort of relative minimum degree is at least the Dirac limit, so with minimum d degree at least this, for any d and k, then this subgraph has a perfect matching. And probably, I mean, I suspect that this this holds as long as p is at least n to the 1 minus k log n, or at least a large constant times 1 minus k to the log n. Yeah, so this is the conjecture, and probably this holds for this small probability, this is precisely the threshold in Shamir's problem for the existence in perfect matchings. Yeah, so I mean, this is obviously a very dramatic strengthening of Shamir's problem, in that, I mean, Shamir's problem is just asking to show that above this probability threshold, my random graph itself has a perfect matching. And here I'm saying that, well, first I sample my random hypergraph, and then I'm allowing an adversary to select a subgraph of that with high minimum degree, and I want that to have a perfect matching. Yeah, and this fact that you need something to hold for all subgraphs, for like an adversarially selected subgraph, this seems to make previous approaches for Shamir's problem not terribly effective. And so I think that if you want to make progress on this conjecture, you need new ideas. You need pretty substantial new ideas. Okay, and so I guess the first of the theorems that I would like to tell you about today, or at least the first of our theorems, is that together with Asaf Ferber, we managed to prove well, this conjecture under some assumptions on P. So namely, as long as P is at least this, and at least this, then we do have a Dirac-type theorem relative to a random hypergraph. Yeah, which of course is not as small as the probability that I conjecture this probably works at, but still this is, I think, very, very non-trivial. I think this is the first general Dirac-type theorem for random hypergraphs. So maybe just to say a couple words about these two assumptions on P. The second assumption here is actually weaker than the first one, unless k equals 3. So yeah, so you only have to worry about this one if k equals 3, and actually this can probably be improved. It's just a little bit fiddly to it's convenient to assume this. The first assumption here is much more fundamental, and I think this is a barrier for a pretty wide class of proof approaches. So hopefully I'll have time to say a few words about why that is, and I think it would be very interesting if one could improve this. Okay, so anyway, that's our theorem. A very simple application of this theorem, and really of when you have any Dirac-type theorem, an almost trivial corollary of that is that you have some bound on packing disjoint perfect matchings. So for instance, a corollary of our theorem is that if you have a random hypergraph whose edge probability is not too small, then typically you can find this many disjoint perfect matchings. And that's just by iteratively. I mean, you find your first perfect matching, you delete it, now you have some subgraph, it's still got high minimum degree, so you can find another perfect matching and just keep going like this to find this many disjoint perfect matchings. Now this observation is not terribly impressive, especially because, well, a few years ago, Ferber and Vu managed to prove much stronger packing theorems for perfect matchings in random hypergraphs. In fact, near optimal packing theorems, both in terms of the proportion packed and in terms of the probability threshold this works at. They did this using Johansen-Kahn-Vu stuff in connection with a beautiful idea called online sprinkling. Yeah, so this observation is kind of rubbish on its own, but it turns out that we can apply these theorems. We can sort of push this kind of observation much further in a much less naive way, and prove some much stronger theorems. So what theorems are those? That brings me to the second part of my talk on resolvability of random designs. Okay, so to briefly introduce this topic, here's a very old problem called Kirkman's schoolgirl problem. I'm led to believe that this is one of the oldest problems in combinatorics. But it says that well, it says that 15 young ladies in a school walk out 3 abreast 7 days in succession, and it is required to arrange them daily so that no 2 shall walk twice abreast. Maybe it's a little bit, takes a moment to interpret what exactly is being asked here. But let me rephrase this question in the language of design theory, because this is really a question about combinatorial designs. I think this is like the genesis of combinatorial designs. Yeah. So an order n Steiner triple system is a 3 uniform hypergraph on n vertices, such that every pair of vertices in this hypergraph is contained in exactly 1 edge. So with the terminology that I just gave you, that means that the degree of every pair of vertices is exactly 1. So it's a kind of a very regular 3 uniform hypergraph. And then I say that a Steiner triple system is resolvable if its edges can be partitioned into perfect matchings. So that means that you have a collection of disjoint perfect matchings such that every edge is in exactly 1 of them. So here's a picture. So here the colored triangles here are supposed to indicate edges in my 3 uniform hypergraph. So you can see that every pair of vertices is contained in exactly 1 edge. So this is a Steiner triple system. And the 4 different colors here each give me a perfect matching. So this gives me a resolution into perfect matchings. Okay, that is what a resolvable standard triple system is. And then in this language, all Kirkman is asking for is for the reader to find an order 15 resolvable standard triple system. I mean, the 15 young ladies are like the 15 vertices of this hypergraph. And the 7 days of the week that you need to arrange them into, you're going to need exactly 7 perfect matchings in a resolution of this standard triple system. Okay, so that's what Kirkman's schoolgirl problem is. This was solved by Cayley, essentially directly after it was proposed. But of course, this is this is not such a serious question. This is, it's a finite. You just have to find a particular object on 15 vertices. It's really more of a puzzle. It was presented as a puzzle. But the question that we would really like to answer, sort of the more serious question here, is that I would like to answer the same question, but with like n in place of, with some general n in place of 15. For which n does there exist an order n resolvable standard triple system? So this more general question is itself usually also called Kirkman's schoolgirl problem, namely to show that whenever n is 3 mod 6, there exists an order n resolvable standard triple system. And this condition that n is 3 mod 6 is, maybe I won't tell you the details of why this is necessary, but clearly this is a necessary condition. And you can see that just by sort of counting things and checking that things are divisible by other things. For example, one obvious thing is that certainly the number of vertices needs to be divisible by 3. Otherwise, you won't be able to find any perfect matchings, let alone a resolution into perfect matchings. Yeah, so this I think was sort of this is a central problem in design theory. For a long time, it was one of the most important open problems until it was resolved independently by Ray, Chaudhry, and Wilson, and by Liu. This was over 100 years after Kirkman had first posed his problem. I should say, by the way, that here I'm talking about standard triple systems and 3 uniform hypergraphs, and there's not really any special significance to the number 3. Standard triple systems are a special case of a more general class of objects called designs. For example, you could talk about like standard quadruple systems. And actually everything on this slide still makes sense for these higher order notions of designs, and most of what I say from now on will still apply to that, but maybe let me focus on standard triple systems, which is sort of the simplest non-trivial case to think about. Okay. Anyway, so the point is that trying to show that resolvable standard triple systems even exist in general is a very difficult problem. But despite this, with Asaf, I guess in connection to our work on perfect matchings in random hypergraphs, we have begun to suspect that actually resolvability is a typical property, meaning despite the fact that it's so hard to find these things, in fact, almost all standard triple systems are resolvable, which, let me remind you, that means that I can partition the edges into perfect matchings. And you can check that if you can do this, you're going to need exactly this many, n-1/2 perfect matchings. Okay, yeah. So this conjecture actually runs in the opposite direction to some very old speculations in design theory. But I think that until very recently, we had an extremely poor understanding of what a typical design might look like. This question is really a question about random designs. It's asking about the typical properties of a uniformly random standard triple system. Let me remark that this study of random designs is one that is of interest in design theory, but it's really a very formidable thing. Like for instance, even the problem of algorithmically sampling, even generating a uniformly random standard triple system is a very difficult problem. In fact, it's an open problem how to efficiently generate a near uniformly random standard triple system. So Cameron has some Markov chain which appears to kind of mix between standard triple systems, but it's an open question whether it's even connected, let alone rapidly mixing. Yeah. So of course, what this means is that even if you want to like empirically look at random designs to just see what properties they have, that's already a difficult. That's already a very difficult problem. Yeah. Okay, so it's very difficult to prove anything, essentially anything about random designs. But there has been a little bit of work related to this conjecture for properties that hold for all standard triple systems. So there are certain things that hold deterministically, and for any standard triple system, and these are mostly proved using the Rödel nibble. So the first thing here is this theorem of Pippinger and Spencer is actually a corollary of a much more general theorem about hypergraph coloring. But it says that in a certain sense, every standard triple system is almost resolvable, in the sense that you can find sort of an asymptotic packing of almost perfect matchings, n over 2 minus little o of n disjoint matchings, each of size n minus little o of n, for some undetermined, for some like undetermined little o of slowly growing, slowly vanishing term, little o of n. Yeah. Perhaps a more classical and question here is, instead of worrying so much about packing, if I ask for a single matching as large as I can find it in an arbitrary standard triple system, you know, how close can I get to a single perfect matching? So there's a number of results that are sort of very old and I haven't written here, but maybe the most famous, or at least for a long time, the state of the art was by Alon, Kim, and Spencer, who proved that every standard triple system has a matching covering all but about square root n of the vertices by sort of analyzing the Rödel nibble in a kind of refined way. And then very recently, this bound was finally improved by Kivash, Pokrovsky, Sudakov, and Yepremyan, introducing some I think very pretty new ideas in addition to the Rödel nibble. To show that you have you always have a matching covering all but at most log n vertices, approximately log n vertices. Okay, so that's some background, and finally, what our contributions are is that well, first, so this theorem is actually from a few years ago. This is actually something I did during my PhD, but sort of took a few years to get published. But I proved that almost every standard triple system does have at least a single does have a perfect matching. And then the more recent result that I wanted to talk about today is that together with Asaf, we managed to push the ideas in this first paper much further, and in particular combine these kinds of ideas with the sort of machinery for Dirac-type theorems in random hypergraphs in order to prove a packing theorem. So as I said earlier, if you want to pack perfect matchings, it's very helpful to have Dirac-type theorems. And so we proved that almost every standard triple system is almost resolvable in a stronger sense, namely that you've got n over 2 minus little o of n genuine perfect matchings. Okay. And so that's the second of the theorems that I wanted to help to tell you about today. I guess I should tell you that I mean I've just gotten done telling you that random designs are really hard things to think about. So how could we possibly prove either of these theorems? Well, in my first paper on this subject, I proved this approximation theorem, which, as far as I know, is still the only sort of general tool that we have for studying random designs. But basically, it gives us some way to take things that we know about ordinary random graphs, binomial random graphs, and transfer those properties to random designs. So I'm omitting some technical conditions here, but more or less, this approximation. Oops, what am I doing? more or less this approximation theorem says that if I have some property which holds with extremely high probability, probably very, very close to 1, so 1 minus about e to the minus n squared, if that's true in an ordinary random hypergraph where the edges are independent, and I want the edge probability to be 1 over n, because this is going to give me roughly the same number of edges that a standard triple system has. If that's the case, then this same property holds with high probability, not as high probability, but still with high probability in a random standard triple system. So this gives some way to attack questions about random designs just by studying the random hypergraphs that we know very well. And I should say that this is a highly non-trivial theorem. This in particular depends on the machinery of Peter Kibosh, which he introduced to study designs. Okay, so sort of one might hope that maybe you can just take the resolution to Shamir's problem, because this probability is 1 over n is certainly much larger than the threshold for the existence of a perfect matching. One might hope to just take the Johansson-Convu theorem and sort of map it to random designs. Unfortunately, this doesn't work because this restriction here is really a very strong restriction. Actually, like almost any property of random hypergraphs that you can think of is not something that holds with this high probability. Very few properties actually do hold with that probability. In particular, the property of even containing one perfect matching. Well, you can't contain a perfect matching if you have an isolated vertex, and an isolated vertex is already far too likely to allow you to use this theorem. So what we need to do is a little bit sneakier. Namely, we need to identify some auxiliary property Q, which is not the property of having a perfect matching. And this property does hold with the sort of the requisite probability, but such that if I combine the property Q with the property of being a standard triple system, well, every standard triple system with property Q does have a perfect matching, or for the second theorem, it has an almost perfect packing of perfect matchings. Yeah. Yeah. So of course, if you're going to take an approach, if you're going to do something like this, in some sense, you need a kind of constructive understanding of why random hypergraphs have perfect matchings, because you can't use the randomness of the random hypergraph directly. You need to identify some deterministic property that helps you find some deterministic consequence of the randomness that helps you find perfect matchings. And so again, just like the Dirac-type stuff, this is another problem where it seems like you need very new, well, very different ideas. Okay, yeah, so we had these two theorems. We have this Dirac-type theorem for random hypergraphs, and we have this theorem that almost all standard triple systems are almost resolvable. Yeah, and as I said, both of the proofs of both these theorems are very closely related, because the way that you're going to do the packing, the way that you're going to pack all these disjoint perfect matchings, is essentially with a Dirac-type theorem for random hypergraphs. Okay, so I have 10 minutes now to tell you about the proofs, which is definitely not enough time to tell you about the proofs, but let me try and say some things. Maybe I should skip telling you about the KLR conjecture. So maybe you do or do not know about the sparse regularity method of the KLR conjecture, but suffice it to say that so this is, maybe let me leave that. This is, the KLR conjecture is a general tool for studying questions in subgraphs of random hypergraphs. Like it's one of these tools that sort of can be used to immediately resolve many extremal problems. It's not suitable for spanning substructures like perfect matchings, but you can use these ideas to find almost perfect matching. So in the setting of this conjecture, in the setting of this Dirac-type conjecture, that if you take a subgraph of a random hypergraph above the Dirac threshold, then you can typically find an almost perfect matching covering like n minus epsilon n vertices for any constant epsilon. So the real problem, and I mean really the meat of what this work is about is finding a way to turn an almost perfect matching into a perfect matching, which was with I guess obviously with the absorption method. Okay, so what is absorption? Well, here is sort of the scheme that one usually does to use absorption in for perfect matchings. Namely, you want to find some kind of absorbing structure X in your hypergraph, which is somehow very flexible and can contribute to perfect matchings in many different ways. And then if you know how to find almost perfect matchings, you're going to find an almost perfect matching in the rest of the hypergraph and use this magical property of X to convert the almost perfect matching into a perfect matching. Yeah. Yeah, so I mean, I've given you almost no details. This is really not that complicated. I mean, it's maybe like a page or two of proof. Yeah, so the absorption method is something. I mean, it was maybe first introduced by Erich Garfasch and Pieber. It was systemized by Rodolitzinski and Samaretti, and as I'm sure you're aware, this is an idea that has since, I mean, tons of people have worked on this and considered tons of variations on different ways that you can do absorption. But I think it's fair to say that almost all of the work on the absorbing method, the way it proceeds, is that you're going to build your absorbing structure using these tiny gadgets called absorbers. So yeah, so you sort of you have these very simple, very small subgraphs, which are simple enough that you can just find them directly by looking at edges and sort of, I mean, directly building these things. And then once you have lots of absorbers, you sort of mash them together in some way to find an absorbing structure, which yeah, that's how one typically does things. Now, I mean, I haven't really given you enough detail to see why this is, but there are many obstacles for generalizing this stuff to subgraphs to subgraphs of sparse random hypergraphs, which maybe some of you have thought about this stuff before and sort of know why. Yeah, so many of these obstacles we were able to overcome. I mean, we were able to prove some stuff about perfect matchings. But one obstacle that we weren't able to overcome, which I think is worth pointing out, is that, well, an absorber, I mean, again, I haven't really told you that much about the absorption method, but sort of the way it has to work is that your absorber has to be a union of two perfect matchings on the same vertex set. So you somehow get a choice to which matching you use. So in particular, it's always going to have density 2 over k, no matter how clever you are about choosing your absorber. So if you know, if I'm trying to be very clever and I come up with my favorite absorber, that absorber is simply just not going to exist in a random graph with edge probability below this threshold. So yeah, so somehow this, so I mean, so this was an assumption we needed to make in our theorem, and this is kind of fundamental if you're in sort of the typical kind of application of the absorbing method. You sort of need to make this assumption, and that's why I think it would be very interesting to improve this. But in any case, you know, provided this assumption is met, we were able to prove a sparse absorbing lemma. So this is a sparse analog of the so-called strong absorbing lemma of Hahn, Persson, and Schacht. And maybe you shouldn't try to read what's on the slide here, but it's just saying that I mean, if I have a subgraph of a random hypergraph above the Dirac limit, then typically it's got the property that I can find an absorbing structure which somehow lets me complete an almost perfect matching into a perfect matching. And this is really what underpins both of the theorems that I talked about today. Okay. Yeah, you can prove some variant of this that holds with really high probability, which is suitable for using this approximation theorem to transfer it to random designs. Yeah. So the proof of this absorption lemma is not, I mean, it's not very easy. It's not, I mean, if you're actually interested, we have an outline in our paper, which is maybe 3 pages, which I think is quite comprehensible. But I definitely don't have time to explain the proof in my remaining 4 minutes. So let me just say some buzzwords, which is, so the first thing is that we need to use this very powerful way to apply absorption called a distributive absorption due to Montgomery. And also perhaps the newest idea is that we somehow need to build absorbers in a non-constructive way. Because, I mean, typically you would like have an explicit absorber in mind that you can like draw a picture of and you'd find that. But we don't actually know what the Dirac limit is. And somehow we need to do everything in terms of this Dirac limit without knowing what it is. So in particular, our absorbers somehow depend on this Dirac limit. So it seems very difficult to sort of do things by hands in that case. So instead, we have some ideas of, I mean, combining the KLR conjecture with some certain contraction tricks in order to find absorbers. Yeah, but maybe let me leave it at that. And let me finish by talking about some further directions. I think there's really a lot of very interesting work that remains to be done here. So the first thing, and I think by far the most interesting direction is to make all this stuff work for smaller values of p, for sparser random hypergraphs. So I don't know if you remember, but for this Dirac-type theorem, we had 2 restrictions on p. This first restriction is probably kind of a low-hanging fruit to get rid of. But the second restriction, as I've been talking about, is less easy to get rid of, and I think it would be very interesting to go beyond this. I think even if, I mean, maybe even forgetting about Dirac-type theorems for now, if you had any way of showing that perfect matchings even exist in a random hypergraph below this threshold, but doing it in a sort of constructive way, I think that would be really interesting. Okay, the second bullet point here is that, well, we've considered perfect matchings, but if you want, you can consider all sorts of different spanning substructures. For example, Hamiltonian cycles. I mean, so the notion of a Hamiltonian cycle doesn't generalize in a super obvious way to hypergraphs, but there are various notions you can consider. And for example, loose Hamiltonian cycles can probably be handled in a pretty similar way to what we did with perfect matchings. Of course, you can consider any kind of spanning subhypergraph you want, maybe subhypergraphs with bounded degree or something, and that's probably hard. This third bullet point here is that, well, we've got some almost perfect packing results, and it would be great to have some genuine perfect packing results. So the first question is maybe in an ordinary random hypergraph to find minimum degree many disjoint perfect matchings, which is actually maybe not perfect packing because there's a variation of the degrees. So even if you have minimum degree many perfect matchings, there's still some unused edges. So this is maybe even something that you can do using Johansson-Kanvu type ideas. But I think it would be nonetheless interesting to do things in a sort of more constructive way, even if for large values of p. And of course, there's this question of showing that almost all standard trivial systems are genuinely resolvable, which I think would be really especially interesting in design theory to prove that in fact resolvability is typical. And finally, I've talked about random hypergraphs. If you want, you can. I mean, it makes sense to consider pseudo-random hypergraphs for various notions of pseudo-randomness, which somehow this is really getting at the same kind of thing that I've been discussing so far. Somehow instead of using randomness, you want to identify consequences of the randomness that allow you to find perfect matchings. And so this is, I think, also an interesting direction to think about. So that's the end of my talk.
Okay, thank you very much. So let us thank Matthew. Okay, we have some time for questions, please.
I have a question. I was just wondering, Matthew, about this absorber you mentioned. You said that the P being around n to the k over 2 comes from the absorbing structure.
Mm-hmm.
Can you say a bit more about that? Like, I mean, you can try to use other absorptions, or what is the fundamental problem there? Like, is it it's difficult to come up with other absorbing structure, or why is there this barrier there?
Yeah, so typically the absorbing structure is itself comprised out of absorbers. Absorber is something on a constant number of vertices, which consists of 2 disjoint perfect matchings. It's like by analogy, if you're thinking about absorbers in graphs, it's maybe like a path which can be matched in 2 different ways. So you want some hypergraph which can be matched in 2 different ways, and that's sort of the building block for your absorbing structure. Which that seems like it seems like somehow you need something which can be matched in multiple different ways in order to do absorption. But if you have 2 disjoint perfect matchings on the same set of vertices, the density of that subgraph is going to be 2 over k. So that's something that's not going to exist in random graphs below this threshold. The key, like what one really needs to do is to find absorbers that are not of constant size. That would be one way to get past this bound. Yeah, but that seems hard.
I see. Okay, yeah, makes sense. Thank you.
Any more questions? Okay, I don't see anything in the chat, so let us thank Matthew once again.